The phrase a circumflex euros overcum of spatia euros suggests a perfect, absolute emptiness, but real cosmic vacuum is more subtle. In physics, a vacuum is any region with extremely low particle density and very low pressure, compared with familiar environments like Earth Euros TM's surface. Interplanetary space around Earth has roughly a few atoms per cubic centimeter. Interstellar space in our galaxy falls to roughly 1 atom per cubic centimeter, and the vast spaces between galaxies may contain only a handful of particles in the volume of a living room. By everyday standards, this is an extraordinary emptiness, yet it is not truly nothing. Particles drift through, radiation streams across, and weak magnetic fields fill much of the volume. Even in the best human-made laboratory vacuums, pressures are still higher and particle densities greater than what is typical in many regions of deep space. The vacuum of space is often portrayed as an instant destroyer of the human body. The reality is dangerous, but in some ways less dramatic than popular fiction. Without a suit, the air in the lungs rushes out in a fraction of a second. Moist surfaces like the tongue and eyes begin to boil gently, not from heat, but because the surrounding pressure is almost zero and liquid water can no longer remain stable. Blood inside the body does not erupt outward because skin and tissues provide structural support, but gases dissolved in the blood can form bubbles, a process similar to decompression sickness. Unconsciousness usually arrives after roughly 10 to 15 seconds as oxygen in the blood is quickly used up. After about 1 to 2 minutes, damage to organs and brain becomes severe and irreversible, particularly from lack of oxygen and swelling in delicate tissues. Stories of astronauts exploding in vacuum are inconsistent with known biology and physics. The human body contains significant water, which is largely incompressible. When external pressure is removed, internal pressure does not suddenly overwhelm the body Euros TM structure. Instead, the body swells by roughly a factor of 2 in volume, limited by elasticity of skin and connective tissue. This distension would be painful and damaging, but not a Hollywood-style detonation. Experiments on animals conducted during the Euros 20th century, though ethically troubling by modern standards, showed that brief exposures of tens of seconds could be survived with rapid repressurization, though with risk of injury. The main threat remains lack of oxygen rather than mechanical destruction by vacuum. Cooling is also slower than often imagined, because heat loss in vacuum occurs mainly through radiation, which operates over minutes to hours rather than instant freezing on contact with emptiness. For inanimate materials, vacuum acts less like a violent hammer and more like a slow, persistent solvent. Many materials contain trapped gases or volatile components. In vacuum, these components gradually escape, a process called outgassing. Plastics, adhesives, lubricants, and paints can slowly lose mass, become brittle, or deposit thin films on nearby surfaces. Some materials absorb small amounts of gas while on Earth and then release it in space, potentially fogging optics or contaminating sensors. Porous materials can also experience subtle structural changes as trapped air pockets vanish. Longer Euros term exposure to vacuum often works together with temperature extremes and radiation. On the sunlit side of an orbit, temperatures can rise above roughly 100 degrees Celsius, while shaded regions can fall below -100 degrees. Repeated thermal cycling can crack coatings and solder joints. Engineers design spacecraft with this combined vacuum, thermal, and radiation environment in mind, treating it as a slow eroder rather than an immediate destroyer. The hazards of space are not due to vacuum alone. In orbit around Earth, for example, spacecraft and astronauts move through a region filled with higher Euros energy particles trapped in the planet Euros TM's magnetic field. Beyond Earth Euros TM's protective envelope, galactic cosmic rays and occasional bursts from the Sun add to the radiation environment. Vacuum removes the shielding that an atmosphere normally provides. On a planetary surface with an atmosphere, most higher Euros energy-charged particles are scattered, absorbed, or slowed before they reach the ground. In space, without air, each particle can traverse long distances, sometimes passing through electronic circuits or living tissue. Over time, this can damage DNA, increase cancer risk, and degrade materials. Some microscopic life forms, such as certain bacteria and tardigrades, have shown the ability to survive temporary exposure to vacuum and radiation in controlled experiments, but only by entering highly specialized dormant states and only for limited durations. In everyday experience on Earth, fire can be a powerful agent of destruction. Space changes the rules. Combustion requires both fuel and an oxidizer. On Earth, the oxidizer is usually oxygen from the air. In a hard vacuum, there is no surrounding atmosphere to provide oxygen, and flames cannot propagate in the usual way. If a tank of fuel and oxygen mix is present, as in rockets or pressurized systems, burning can still occur, but only as long as those reactants remain confined together. When stories describe objects burning up in space, what they usually refer to is re-entry through an atmosphere. As a spacecraft or meteor plunges into air at high speed, friction and compression heat material, causing ablation and bright emission. Far from planets and stars, in deep interplanetary or interstellar space, there is simply too little material to sustain the familiar destructive power of ordinary fire. As one moves to larger cosmic scales, the vacuum between stars and galaxies becomes more dominant. In the disk of the Milky Way, the average density of the interstellar medium is roughly 1 hydrogen atom per cubic centimeter, though it varies significantly between clouds and more rarefied regions. Between galaxies in a cluster, the density can fall to roughly 1 particle per cubic meter, while colossal cosmic voids spanning tens of millions of light-Euros years may contain so few atoms that meaningful averages become difficult to define. Yet even these nearly empty regions are not entirely quiet. They host extremely thin plasmas, faint magnetic fields, and streams of higher Euros energy particles. Starlight and the cosmic microwave background permeate them. Rather than acting as an active destroyer, this thin medium functions more like a background canvas on which the brighter, denser structures of galaxies and clusters are painted over immense spans of space and time. On microscopic scales, the concept of vacuum takes another turn. In quantum field theory, even the lowest Euros energy state of a field is not a static nothing. Instead, fields undergo constant fluctuations, producing transient pairs of particles and antiparticles that pop into existence and then annihilate over very short times. These quantum vacuum fluctuations have measurable consequences. The Casimir effect, observed in laboratory experiments, shows that closely spaced metal plates in vacuum experience a tiny attractive force, which can be explained as a change in the allowed quantum fluctuations between them compared with outside. The energy associated with the quantum vacuum is difficult to define precisely and remains a subject of ongoing research. Some hypotheses link vacuum energy to dark energy, the unknown component thought to drive the observed acceleration in the universe Euros TM's expansion, though simple estimates of vacuum energy overshoot observations by enormous factors and highlight unsolved theoretical challenges. On galactic and larger scales, the lower Euros density vacuum between structures can be thought of as a medium in which gravity sculpts matter. Where density is slightly higher, gravity pulls more strongly, drawing in gas and dark matter and forming galaxies and clusters. Where matter is slightly more rarefied, expansion effectively evacuates regions further, eventually producing larger Euros-scale cosmic voids. Vacuum, in this sense, does not destroy matter so much as separate it, allowing overdense regions to evolve largely on their own. Inside galaxies, supernova explosions and stellar winds push gas outward, sometimes driving it into intergalactic space. Over billions of years, galaxies can lose a portion of their gas this way, reducing their capacity to form new stars. The surrounding lower Euros density environment provides little resistance, so once material is pushed out, it can travel extensive distances before gravity or collisions incorporate it into another structure. Near black holes, gravity shapes space and time so strongly that familiar intuitions about vacuum begin to fail. Outside the event horizon, densities can be quite low, forming a hot, diffuse plasma rather than a solid surface. Yet the spacetime curvature is intense. General relativity predicts that nothing, not even light, can escape from within the event horizon once crossed. Around many black holes, matter forms accretion disks, which can heat to millions of degrees Kelvin and radiate intensely in Euros rays. In a sense, a black hole combined with surrounding vacuum acts as an efficient sink for matter and radiation. Over very long timescales, black holes are predicted to emit Hawking radiation, slowly losing mass. For stellar Euros mass black holes, this evaporation time far exceeds the current age of the universe, so observational confirmation remains challenging. Nonetheless, they illustrate how gravity and vacuum together can confine and eventually disperse energy. Looking ahead over timescales far beyond human history, the interplay between vacuum and matter becomes central to some models of the universe. Euros TM's longer Euros term future. If current observations of accelerated expansion continue to hold, galaxies beyond the local group will gradually recede beyond our observable horizon. Over roughly trillions of years, star formation will decline as gas reservoirs are consumed or expelled. Existing stars will burn out, leaving white dwarfs, neutron stars, and black holes. Interactions and quantum processes may slowly erode even these remnants, dispersing matter as lower Euros energy radiation and subatomic particles. In this lower Euros called heat death scenario, the universe approaches a state of maximum entropy, where energy is spread so thinly and uniformly that no larger Euros scale structures can do meaningful work. The result would be a cosmos dominated by extremely cold, dilute radiation and an almost featureless vacuum. Considering these scales together suggests a nuanced answer to whether the vacuum of space can destroy everything. On human scales, vacuum is immediately hazardous by removing the air and pressure that our bodies and technologies rely on, yet it does not produce instantaneous, explosive destruction. Over spacecraft lifetimes, vacuum contributes to gradual material degradation, working with radiation and temperature extremes. On galactic scales, vacuum separates structures but does not erase them. Over the longest conceivable times, under some cosmological models, the expanding, increasingly empty universe might evolve toward a state where complex structures can no longer form or persist. In that limit, destruction is less an act of violent removal and more a slow dilution of energy into an ever Euros colder, ever Euros more tenuous background. The vacuum of space, far from being simple nothingness, is an active participant in the unfolding history and eventual fate of matter and energy. To look deeper into whether the vacuum can destroy everything, it helps to return briefly to the beginning of cosmic time. Cosmologists study a proposed phase called cosmic inflation, when the very early universe may have expanded at an extraordinarily rapid rate. In most mainstream models, this expansion is driven not by ordinary matter, but by a form of vacuum energy associated with a higher Euros energy quantum field. In that picture, empty space itself contains stored energy whose pressure is negative, meaning it pushes space to expand rather than allowing gravity to pull it together. During inflation, this vacuum energy would dominate over all other contents and stretch even tiny quantum fluctuations into seeds for later galaxies. When inflation ended, that energy would have been converted into particles and radiation. Here, vacuum does not destroy structures because no structures exist yet. Instead, vacuum energy shapes the conditions from which structure later emerges. The idea that vacuum can hold energy returns in modern cosmology under the name dark energy. Observations of distant supernovae and the cosmic microwave background indicate that the current expansion of the universe is not slowing under gravity, but very gently accelerating. The simplest explanation is a small, nearly uniform energy density associated with empty space, described mathematically as a cosmological constant. This energy density is extremely low, roughly 10 to the -9 joules per cubic meter, yet because it fills all of space, it dominates the dynamics of the cosmos on the largest scales. In everyday environments, it has no measurable local effect on materials or living things. Its influence is seen only over billions of lighter Euros years and billions of years, where it gradually overcomes the mutual attraction of galaxy clusters. In that sense, vacuum energy does not rip objects apart directly. Instead, it slowly dilutes their larger Euros scale connections. If dark energy remains constant in time, the far future of the universe acquires a gently isolating character. Galaxies that are not gravitationally bound to ours will recede faster and faster, eventually crossing a horizon beyond which their light can never reach us. Over timescales of roughly 100 billion years and beyond, the observable universe around our descendants, if any exist, would shrink to include only the local group, and later its merged remnant. On smaller scales, gravity within galaxies and within bound systems like solar systems and planets should remain stronger than the extremely weak influence of dark energy. Stars will still burn according to their nuclear fuel reserves, planets will still orbit their suns, and compact remnants will still circle in their dark halos. Here, the vacuum does not directly unmake existing structures. It simply stretches the intervening emptiness so that structures become islands in a deepening cosmic sea. Some speculative models go further and propose that the energy of the vacuum might not be constant. In scenarios labeled phantom energy, the pressure of dark energy is even more negative than in the cosmological constant case. If such a component dominated, the cosmic acceleration would not just continue, it would steepen with time. Mathematical extrapolations of these models lead to a possible cosmic finale, often called the Big Rip. In that picture, the expansion rate eventually grows so rapidly that it overcomes every binding force in turn. First galaxy clusters, then galaxies, then solar systems, and finally even molecules and atomic nuclei are torn apart by the runaway stretching of space. Current observations disfavor the most extreme phantom models, but do not completely exclude slight deviations from a pure cosmological constant. If a Big Rip were real, the agent of destruction would again be vacuum energy, acting through the expansion of space rather than traditional mechanical tearing. Beyond changing density, theorists consider another possibility tied to the quantum nature of fields. In quantum field theory, the vacuum of our universe might not be the absolute lowest energy state possible. It could be metastable, like a ball resting in a shallow valley when a deeper valley exists nearby. This configuration is often called a false vacuum. If a lower energy, true vacuum state exists, the universe could, in principle, undergo a transition. Such a shift would involve the spontaneous formation of a tiny bubble of the new vacuum, somewhere in space, by a rare quantum fluctuation or through higher Euros energy processes in the very early universe. Inside the bubble, the values of fundamental fields, such as the Higgs field, could differ from their familiar values. Because particle masses and interaction strengths depend on these fields, the very rules that govern atoms and nuclei might change across the bubble boundary, with far Euros reaching consequences. The physics of a hypothetical vacuum transition is usually described using the language of bubble nucleation and growth. When a bubble of lower Euros energy vacuum appears, it initially forms at subatomic scales. If the new vacuum truly has lower energy, the difference in energy density between inside and outside drives the bubble to expand. Calculations based on relativity suggest that, in the frame of the old vacuum, the bubble wall would rapidly approach the speed of light. There is no known mechanism to halt its growth once it begins. As the wall passes through a region, the local form of matter and the forces holding it together would encounter new values of the underlying fields. In many models, ordinary matter becomes unstable or simply cannot exist in recognizable bound states under the altered constants. To observers in the old vacuum, there would be no forewarning. The transition front would arrive and, in less than a heartbeat, rewrite the local physics. The specific outcome of a vacuum transition depends on unknown details of higher Euros energy physics, so any description must be cautious. However, studies using plausible ranges for how constants might shift suggest that familiar structures are fragile. If the Higgs field value changed significantly, the masses of electrons and quarks would change. Atomic energy levels depend sensitively on the ratio of electron mass to nuclear charge. A sizable shift could prevent electrons from forming stable bound orbits, erasing the periodic table as we know it. If the strength of the strong nuclear force were altered beyond modest bounds, protons and neutrons might not bind into nuclei, or nuclear fusion and fission rates could change drastically. Even small fractional changes in fundamental couplings often lead to large qualitative changes in what kinds of atoms and molecules can exist. In many scenarios, complex chemistry and thus life would be impossible in the new vacuum. Although a vacuum transition sounds catastrophic from the perspective of our familiar physics, the event might not resemble an explosion in the conventional sense. Inside the bubble of new vacuum, space would be quiet and uniform, just governed by different field values and perhaps different particle content. The destructive aspect arises only because structures encoded by the old vacuumer, Euros TM's constants, cannot survive the change. If new constants still permit some form of stable matter, new kinds of atoms and possibly stars could emerge over cosmic timescales within the transformed region. From a local point of view within that new vacuum, the laws of physics would appear internally consistent. A civilization arising entirely inside it would regard its vacuum as normal. The drama lies in the boundary crossing. As the bubble overtakes an area, continuity is broken for observers tied to the old vacuum pattern. Their material arrangements simply lose their meaning. The natural question about vacuum decay is how likely it is. The rate depends on the detailed shape of the potential energy function associated with fundamental fields, which is not fully known. Using the measured mass of the Higgs boson and the top quark, some analyses suggest that our vacuum may be metastable, but with an extremely long lifetime, far exceeding the current age of the universe, by a factor of many trillions or more. Other analyses, incorporating theoretical uncertainties and possible new physics at high energies, find that the vacuum could in fact be absolutely stable. At present, the balance of opinion is that even if metastable, the vacuum is sufficiently longer lived that vacuum decay is effectively irrelevant for any realistic planning or concern. No known astrophysical event, particle accelerator, or cosmic ray appears capable of appreciably increasing the transition probability compared to its already tiny natural value. The remote possibility of triggering vacuum decay has occasionally been discussed in relation to powerful human machines, such as particle colliders. Detailed safety studies compare the energies and densities reached in those devices with natural higher energy collisions occurring in the universe, such as cosmic rays striking neutron stars or white dwarfs. Observations of these dense astrophysical bodies imply that vastly higher energy densities have been sampled many times without apparent destabilization of the vacuum. If vacuum decay were easy to trigger, the universe would likely have transitioned long before humans appeared. Consequently, physicists working with accelerators accept that their experiments probe only a tiny, safe corner of parameter space. The vacuums created in laboratory chambers are higher quality absences of gas, not alterations of the underlying quantum vacuum state. They pose hazards due to pressure differences and material stress, but not due to any change in the fabric of physical law. Across all of these scenarios, from dark energy to possible vacuum decay, a pattern emerges. The vacuum of space is not a simple destructive agent that actively tears apart everything it touches. The near perfect emptiness between stars and galaxies suppresses combustion, corrodes some materials, and exposes life to unshielded radiation. Yet it also allows planets to orbit, galaxies to rotate, and light to travel largely unimpeded. On cosmological scales, a small vacuum energy component shapes the expansion history, gradually isolating structures without disassembling them from within. Only in the most speculative models, where the quantum vacuum changes its fundamental character, does empty space threaten to erase the very possibility of complex matter. Even there, the transformation would be instantaneous for those affected and undetectable in advance. In practical terms, the vacuum is better understood as an arena and an influence than as an active universal destroyer. To continue, it helps to think about where vacuum begins and ends on the largest scales. In standard cosmology, space is often described as spatially infinite, or at least so large that for all practical purposes it might as well be. Within this framework, vacuum is not a container with a hard outer wall. There is no observed edge where matter stops and pure emptiness begins. Instead, there is a gradual thinning. Galaxies cluster, then superclusters, and between them lie filaments of gas and dark matter stretching across hundreds of millions of light-years. The voids between these filaments contain far fewer atoms than the cosmic average, but they still share the same underlying quantum vacuum state. When we ask whether vacuum can destroy everything, we are really asking about processes that could operate everywhere without boundary across this diffuse but continuous cosmic web. The idea that the vacuum might have multiple possible states leads naturally to the concept of domains. In some models of higher energy physics and cosmology, the early universe could have cooled into different vacuum states in different regions, separated by domain walls. Each domain would have its own vacuum expectation values for fields and possibly different values of fundamental constants. Observationally, our observable universe appears remarkably uniform, which constrains how such domains if they exist, could be distributed or how long any domain walls could have survived. Some scenarios of eternal inflation imagine an even more elaborate structure, where new inflating regions continually spawn, each relaxing into its own vacuum state. In that picture, destruction is not so much a single catastrophic event as ongoing cosmic selection. Most vacua would be unsuitable for complex structures, while a subset, like ours, would permit chemistry, stars, and the emergence of observers. Although theoretical arguments can suggest metastable vacua and domain structures, observations place important limits on how unstable our vacuum can be. The age of the universe, roughly 13.8 billion years, already tells us that if vacuum decay or domain wall annihilation is possible, its characteristic timescale must be long compared with this cosmic age. Otherwise, the probability that we would still occupy this vacuum today would be extremely small. Measurements of the cosmic microwave background, with its smooth temperature variations at the level of 1 part in 100,000, show no sign of abrupt boundaries or scars that larger Euro-scale vacuum transitions might have left. Precision tests of particle physics, such as measurements of the Higgs boson mass and sulfur-Euros coupling, further constrain models. Together, these observations suggest that if our vacuum is metastable rather than absolutely stable, it is at least longer Euros lived on timescales vastly exceeding current cosmic history. In the very early universe, temperatures were so high that the structure of the vacuum itself could have been different from today. Thermal fluctuations at energies far above those now accessible in laboratories may have effectively erased barriers between possible vacuum states, allowing transitions that are currently forbidden or fantastically rare. As the universe expanded and cooled, different fields settled into particular configurations, locking in the vacuum structure we experience. This process of cooling through various symmetria Euros breaking transitions is still an area of active research. It affects how we think about potential future changes. On extremely long timescales, the universe will cool even further, approaching a state where matter is thinly spread and radiation is redshifted to very low energies. At such low temperatures, thermally driven changes to the vacuum become even less likely, reinforcing the notion that whatever vacuum state survives to that epoch will tend to persist. Any ultimate assessment of whether vacuum can destroy everything must pass through quantum gravity, a regime where our best current theories are incomplete. General relativity describes gravity as the curvature of spacetime, while quantum field theory treats the vacuum as a fluctuating sea of fields within that spacetime. At energies near the Planck scale, roughly 10-19 gigaeuros electronvolts, these descriptions are expected to merge into a deeper framework not yet fully known. Candidate theories such as string theory and loop quantum gravity suggest that what we call vacuum might arise from more fundamental structures, like compact extra dimensions or discrete quantum geometries. In some of these models, transitions between different vacua are related to changes in the shape or size of extra dimensions or in the topology of spacetime itself. Each possibility carries its own implications for stability, but without experimental access, our confidence in specific scenarios remains limited. Another concept that touches the destructive potential of vacuum is cosmic censorship, a conjecture in general relativity. It proposes that singularities formed by gravitational collapse are hidden behind event horizons, so that distant observers never see the full breakdown of physics at a singularity. If true, this principle would shield the wider universe from certain extreme forms of destruction, confining them within black holes. The vacuum outside would remain well Euros behaved, even as matter disappears into regions where known physics fails. Although cosmic censorship is not mathematically proven in general, many numerical simulations of gravitational collapse support its broad outline. In this picture, vacuum does not act as a universal solvent grinding down reality. Instead, it coexists with localized extremes, allowing structures to form and persist, while the most violent breakdowns of spacetime occur behind horizons, largely disconnected from the wider cosmic environment. When discussing destruction in a deep sense, it is natural to consider information. Even if matter survives for a long time, randomization and dispersal can effectively erase structure. Black holes, Hawking radiation, and the fate of information are central themes in modern theoretical physics. If black holes eventually evaporate, as most calculations suggest, the universe may evolve toward a state where matter and energy are spread thinly as lower energy particles and radiation. The vacuum would then be nearly empty, but not completely blank. There is ongoing debate about whether information that falls into black holes is preserved in subtle correlations in their radiation or lost entirely. Current consensus leans toward preservation, consistent with quantum theory, although the precise mechanisms are still being explored. In any case, the vacuum of a far future universe would contain a record of its past only in extremely diffuse, practically irretrievable form. The interaction between vacuum and destruction also relates to the arrow of time. The observable universe began in a state of low entropy compared with what is possible for the same total energy. As it expands, gravity helps matter clump into stars and galaxies, temporarily decreasing entropy locally while increasing it overall. Over very long periods, these structures burn their fuel, collapse, and disperse. The vacuum between them appears ever more dominant. Yet the arrow of time is not set by vacuum alone. It depends on boundary conditions, such as the initial lower entropy state at the Big Bang. Some speculative ideas suggest that the vacuum might fluctuate into new lower entropy regions, potentially giving rise to new cosmic histories. Others argue that such fluctuations are extremely rare or conceptually problematic. What remains clear is that the presence of largely empty space provides the stage on which entropy can increase, but it does not, by itself, force a particular direction. Even in an almost empty universe, subtle structures can emerge from the properties of vacuum and the fields it contains. For example, topological defects such as cosmic strings or domain walls, if they exist, would be configurations of fields stabilized by the vacuumer TM's geometry in abstract field space, not by material support. In condensed matter physics, analogues of vacuum phenomena appear in superfluids and superconductors, where an ordered ground state allows excitations with properties unlike those of the underlying particles. These systems show that a seemingly featureless ground state can support rich emergent behavior when slightly disturbed. By analogy, the cosmological vacuum may harbor possibilities for patterns and excitations that we have not yet fully imagined, especially if new fields or interactions are discovered. Rather than a simple destroyer, vacuum can be viewed as the quiet background from which complexity rises, persists for a while, and eventually fades. Turning from cosmic scales to human technology, the controlled creation of high vacuum has become an essential tool rather than a threat. In particle accelerators, ultra high vacuum, often at pressures below 1/1,000,000,000 of Earth TM's atmospheric pressure, reduces unwanted collisions between accelerated particles and stray gas molecules. This allows beams to maintain their energy and focus over long distances. In space simulation chambers, engineers test satellites, instruments, and materials under vacuum conditions combined with temperature extremes, helping to ensure that hardware can survive launch and operation. Electron microscopes rely on vacuum to allow electrons to travel unimpeded from source to sample, revealing structures at nanometer scales. In all these cases, vacuum is carefully managed and separated from vulnerable human operators by layers of engineering. Rather than destroying, it enables insights into Materia TM's structure and behavior that dense environments would obscure. Although complex multicellular organisms like humans cannot survive unprotected exposure to hard vacuum, some forms of life show surprising tolerance to near-Euro's vacuum and harsh space conditions. Certain bacterial spores, lichens, and microscopic animals known as tardigrades have been experimentally exposed to low Earth orbit conditions, including near-Euro's vacuum, intense ultraviolet radiation, and temperature swings. A fraction of these organisms survived, especially when shielded from direct sunlight or partially embedded in protective material. Their survival strategies rely more on desiccation resistance and DNA repair than on direct adaptation to vacuum itself. Nonetheless, these experiments demonstrate that life is not instantly erased even by combined stresses that approximate interplanetary space. Over geological timescales, such robustness raises the possibility of natural transfer of microorganisms between bodies, a concept known as lithopanspermia. Here, vacuum functions more as a challenging transit environment than an inherently destructive agent that guarantees sterility. In the end, when we consider whether the vacuum of space can destroy everything, we are also reflecting on timescales and meaning. On human timescales, vacuum is a hazard but manageable. Spacecraft, suits, and habitats keep pressure where it is needed. On stellar and galactic timescales, vacuum shapes evolution by limiting where matter can gather and by allowing radiation to stream freely, cooling and spreading energy. On cosmological timescales, expanding vacuum and dark energy may gradually thin out structures, erode gravitational binding, and lead toward a state of profound simplicity. Whether this counts as destruction depends on perspective. The underlying quantum vacuum may persist, perhaps indefinitely, perhaps not. Matter, radiation, and information may become diffuse and cold. Against that vast backdrop, the structures that briefly arise, including living beings and their thoughts, are fleeting patterns in an immense, quiet sea of almost nothing. As understanding of the vacuum deepens, what stands out most is how many questions remain open at a quantitative level. Measurements of dark energy TM's density, for example, carry uncertainties of a few percent and rely on models of supernovae, galaxy clustering, and the cosmic microwave background that are still being refined. The underlying microphysics of inflation, if it occurred, is not yet tied to a specific, experimentally verified particle theory. Even the zero level of vacuum energy in quantum field theory is ambiguous and must be renormalized in ways that obscure a direct link to the observed cosmic acceleration. At smaller scales, attempts to merge quantum theory and general relativity must specify how vacuum fluctuations gravitate, yet different candidate theories of quantum gravity can give different answers. In this sense, the vacuum is not only a medium for destruction or creation, but also a quiet boundary where current knowledge gives way to carefully quantified ignorance.